the zeros that are part in common, the ones they have part in common. When this increases, this increases. When this decreases, this decreases. And they verify the definition for family resonance. These are one positive and one negative example. Take this sigma, take this mu. Of course, the intersection of the zeros is this interval, 0, 2, then that is not empty. And the intersection of the ones, this is the ones of that, and the only one of mu is that, the intersection is this point, 0. Then this sigma and this mu show family resonance. In this case, there is no family resonance. Look, this is lambda, this is mu, the ones of lambda and the ones of mu, intersection is the same, and there is no family resonance. These two fuzzy sets that do not show my definition of family resonance. This is absolutely easy to prove that observation FR is reflexive and symmetric, but it's not transitive. This is not strange. It happens in families, people's families. John resembles Peter, Peter resembles Joe, but John does not resemble Joe. There is no transitivity. Remember that this idea of Jay, John resembles Peter, is that Jay has an air of family to Peter. I don't know if air of family is a standard phrase in English, but I think you can understand the idea. They have an air of family. They have a resemblance in the family. Okay. Now let me show this counterexample to show that it's not transitive. Look, this sigma, this mu, show family resonance. The zeros and the ones, they have no empty intersection. When this increases, this increases. When this decreases, this decreases. The same between lambda and sigma. They have family resemblance. The intersection of the one is not zero. The intersection of the zeros is not empty. And when this increases, this increases. When it decreases, decreases. Then there is family resemblance between that and that, between that and that. Of course, there is no family resemblance between the mu and the lambda, because they have no zeros in common. Then this relation FR is reflexive and symmetric, but is not transitive. Okay. Hence, FR is not an equivalent relation. There is not a quotient set. There is not. Anyway, I will call the family of mu those fuzzy sets in F star that show family resemblance with mu. And I will call sigma a relative of mu. Of course, sigma would have relatives in other families, because this is not a partition. I have no partition of the sacrifices. These three theorems are scientifically proven. For no component, the strong relation. For no component, mu shows family resemblance with not mu. For no opposite of this type, of course, this is a symmetry in the universe. For no opposite, the mu shows family resemblance with the opposite. Big and tall cannot show family resemblance. If this is a function in the universe that is increasing, that changes the inverse, changes the set of zeros into zeros, and sending the set of ones into ones, then the couple mu and the composition of mu with 1 and minus 1 show family resonance. In particular, as in a lot of cases, this is a synonym of that. If this is a synonym of P, then the P and P and the synonym show family resonance. Let me show examples. This is mu, and this is a complement with the relation 1 minus x. Of course, the set of ones is empty, intersection is empty, and there is no family of resemblances. This is a case of opposites of antonyms. This is mu, and sigma is obtained from mu with this symmetry in the universe 0, 10. Of course, the set of ones is the intersection is empty, and there is no family of resemblances. This is an example of the last theorem. I have this, and I obtain sigma by this transformation. Of course, this transformation is where ux equal x squared changes the ones and ones into zeros. And of course, there is family resemblance between these two, because there is no empty intersection with zeros, there is no empty intersection with 1, and this increases, and it is of fuzzy sets show family. Well, let me enter in the main point of the lecture. Imagine that sigma 1 and sigma 2 are relative of mu. Okay, but this doesn't mean that they show the same degree of angular resemblance with mu. The idea of angular resemblance as a crisp relation is a too, a too ingenuous idea, too naive idea. Fast logic, what we need is numbers. It is a degree of angular resemblance. How I arrived to this maybe a little bit strange idea of first defining a crisp relation and after a degree, because in my brain this is turning and turning for a lot of time, and I try to define directly what is a degree of family resemblance. A degree of family resemblance should be an indistinguishability. But which one? Which one? And only when I decided to start with a clear relation and then define, I see something clear. But before, for me, everything was dark. Okay. Then I will try to define a degree up to which sigma resembles mu. How to find a degree? I was playing for a lot of time with two ideas. It is to take, I was working with a product distinguishability, and I was trying also with a W Lukasiewicz distinguishability. Which one was the problem? The problem was, I will show you in a lot of examples, that the product distinguishability was in most of the cases too low. This indistinguishability gives a too low value, and the W distinguishability this gives a too high value. Then the idea came to my mind to make a mean, an average of both values. Which was the problem? That the average of two indistinguishabilities in general is not an indistinguishable. And this was my problem, to arrive to find a degree being an indistinguishability for some denominator. Okay. This is a theorem by Shinnikov, to be published in 1984, and he said that E is an indistinguishability related to the binomial prod, if there exists a family of functions that are strictly positive, and then this is defined in this way. The infimum for all functions in the family of these quotients. Look, F mu, F sigma, A mu. This is a theorem by Shinnikov. Of course, if this is a protein distinguishability, since the denorm of Lukasiewicz is less than the denorm product, then this is also a W indistinguishability. The problem comes because this is a W indistinguishability, but it's not a protein distinguishability.